Assalamualaikum and hi everyone. So in this video we are going to see one more example of solving the BVP using finite difference method. Okay, so this time we have the BVP, okay, the boundary value problem, very simple. Y double prime equals Y with the boundary conditions Y prime 1, okay, at the left, and at the right you have Y prime 3. Okay, so in this example, both boundary conditions involve the derivative term at the left side as well as at the right hand side. Okay, and then use H equals 0.5. All right, so the first step is to draw the grid of solution. So it means we will have, okay, so based on the boundary conditions that you can see, then we can, sketch our points accordingly. So the x naught is equals 1, okay, because you can see your left point, your left boundary says y prime 1, so you know your left node, okay, is x naught equals 1, and x increased by h, so you have x1 is 1.5, and somehow you know that you must stop at x equals 3, okay, based on the right boundary condition. So you will have more here. So x2 equals 2, and we have here x3 equals 2.5, and x4 equals 3. So we will stop at x4, okay. And then the corresponding y then should be, here we have y naught, and this is y1, y2, y3, and y4. Okay, so for this example, so the left boundary here says that you have y prime 1, okay, equals 1.175. Okay, so basically you cannot put y naught equals 1.175. So this is wrong, okay, because the boundary, what you have over there is y prime 1. That is not y1. Okay, that is y prime 1. So if you put y naught equals 1.175, so it means y1. y1 equals 1.175, which is not in this case. Alright, so it means y naught here is unknown at this moment, at this stage. Okay, y1, y2, y3, of course, are your unknown as well. So the same thing at the right boundary here, you have y prime 3. Okay, so again, you cannot put y4 equals 10.018, okay, because you have y prime 3, that is not y 3. But somehow if your question give you y3 here, then yes, you can put y4 here is 10.018. Okay, but for this one, this is not the case. Okay, all right. Okay, never mind. All right. Okay, so basically we have 5 unknowns here, 5 value of y that need to be determined. Okay, so based on our grid here, and then step number 2 is to discretize the boundary condition that contains the derivative. So we need to discretize both of the boundary conditions. Okay, so let us look at the first one, where we have y prime 1 equals 1.175. Okay, in terms of subscript, okay, subscript, y prime 1 basically is y naught prime. Okay, because y prime 1 is basically the value of y prime when x is 1. So here, so the corresponding y prime here should be y naught prime. Okay, so this is 1.175. Okay, we simplify in terms of notation, y naught prime. And then by the centered difference formula for the y prime, So this is the general formula. Yi prime is yi plus 1 minus yi minus 1 over 2h. Okay, so now back to our left boundary condition here. Y naught prime equals 1.175. So y naught prime here, okay, this guy here, you map to yi prime here. So you know that your I equals 0. So what happened is now we are going to replace this one with the right expression here with I equal to 0. So what happened is you will have here y1 minus y negative 1 because your I is 0 over 2h equals 1.175. Okay? Okay, next. Since we know our h is 0.5, so you are going to replace that with 0.5, and then we isolate y negative 1 to be at the left hand side. Okay, again the idea is to isolate the term that out of our grid of solution. So y negative 1 is somewhere here, which is out of our grid of solution, so we take out that node. Okay, y negative 1, so rearrange the equation, we will come out with y1 minus 1.175. So put this one as equation A. We'll refer to that later. That is your left boundary. Okay, now move to the right boundary, which says that y prime 3 equals 10.018. Okay, next we rewrite in terms of subscript notation. So y prime 3, so x equals 3. So the corresponding subscript is 4, as you can see in your grid of solution. So this is actually y4 prime equals 10.018. So again, in terms of finite difference formula, so we map to this formula here. Okay, so you map to y4 prime, so you know here your I is 4. So based on the finite difference formula, so y4 prime is equal to the y5 minus y3 over 2h equals 10.018. So similarly, we replace our h here with 0.5, and then what we want to have here is to isolate y5. Why we need to isolate y5? Because y5 again is out of our grid of solution. So y5 equals to 10.018 plus y3. So put that as equation B. Okay, so somehow later you will use these two expression here. Okay, next. Discretize the ODE in a finite difference form. So whenever you have the y prime, so you are going to replace with this expression, and then for the y double prime, you are going to replace with this. Okay, so back to our ODE. So what do we have here? So this is our differential equation, y double prime equals y. Okay, so we don't have the y prime, so it's okay. Okay, so we just replace for the y double prime here. So at the right hand side here, you are going to write as y sub I only. So y double prime then, okay, so what you're going to write here is yi minus 1 minus 2yi plus 1 over h square. So that is at your left hand side of the equation. At the right hand side, okay, equals y, so you're going to just write y sub I. Okay, and then what we can do is to rearrange the expression, because in our mind, okay, we should think of forming a linear system. Okay, so you know you have yi at the right hand side as well as at the left hand side, which can be grouped together. Okay, so what we can do now, yi minus 1 minus 2yi plus yi plus 1 minus h square yi equal to 0. again, okay, our intention is to put all the terms that involve the y should be at the left hand side, okay, and the rest put at the right hand side. Okay, so since all of the terms that we have in our equation here involve the y, so everything need to be on the left hand side. So what happened to the right hand side is just 0. Okay, and then okay, we can simplify further. You can group together yi term. Okay, so now yi minus 1, so negative 2, and here we know our h again is 0.5, so you can simplify this guy here. Okay, 0.5 square, and then group together with the negative 2. So you have negative 2.25 yi plus yi plus 1 equal to 0. So what is your I? I start from 0, 1 up to, so you can refer to your grid, okay, based on how many unknowns that you want to get. Okay, so I equals 0 up to 4 in this case. All right, so in terms of molecule diagram, if you want to sketch in terms of molecule diagram, so that you will have yi minus 1 here, and then minus 2.25, so this is yi, and then this is yi plus 1. Okay, somehow the coefficient is very simple. Okay, the right hand side term also is just 0. So the coefficient here is 1. Here you have negative 2.25, so this is plus, and then this is 1. Okay, so very simple. So next is to form a linear system, okay, based on the molecule diagram that you have here. Form a linear system A y equals b. So basically we will start with I equals 0. Okay, because our aim here is to get y naught. Okay, your I start from 0. Okay, y1, y2, y3, and y4. Okay, so 5 unknowns here, so somehow you'll get the hint that you will end up with a 5 by 5 system somehow. So when I equal to 0, so what happened to your expression in your molecule diagram here? So the coefficient is 1, and multiply with your y, so your y will be y negative 1. Okay, you will end up with y negative 1. Okay, y negative 1 minus 2.25 y naught plus y1 equal to 0. So you see y negative 1 here somehow is not in your aim list here. Okay, but in second step just now, we have the expression for y negative 1. Okay, where just now this is E. Expression of A. So you can put back here your A this now is y1. Okay, so you can refer back to the expression of A just now, y1 minus 1.175. Okay, if you want to check together. Okay, so this is A. Okay, y negative 1 can be replaced with this. Okay, so that the term that you will see is something that you have in your grid of solution. So y1 minus 1.175 minus 2.25 y naught plus y1 equal to 0. So again, we can simplify further because we can see we have 2 times of y1. So this is 2 and then 2y1. Okay, but first we put the y naught first. So negative 2.25 y naught plus 2 times y1, and the known value you put at the right hand side. Okay, so this negative 1.175 here, so you put at the right hand side, so it will be like that. So now this is equation 1. Okay, and then you proceed when I equals 1. Okay, when I equals 1, so again based on this molecule diagram, so this guy here will be y 0, 1 minus 1. Okay, so the coefficient is 1 somehow. So this is y0 minus 2.25 y1 plus y2 equals 0. Okay, and there's nothing that we can replace here, so all of the y terms are our unknown. So just put that equation as equation 2, and then when I equals 2, we have y1 minus 2.25 y2 plus y3 equal to 0. So this is equation 3. And then when I equals 3, okay, we have y2 minus 2.25 y3 plus y4 equal to 0. Okay, put that as equation 4. And lastly, when I equals 4, so C will end up with a y3, okay, y3 minus 2.25 y4 plus y5 equal to 0. Okay, so again, y5 is not in our aim list, and somehow this is your expression of B. Okay, so refer back to the second step. So what you can replace, okay, so y3 minus 2.25 y4. So at the y5 here, you replace with the expression of B, which is 10.018 plus y3 equal to 0. And then y3 and y3 here can be simplified further. So you have 2. So I put here, okay, 2y3 minus 2.25 y4, and then the known value you put at the right hand side. So 10.018. So when you put at the right hand side, so it becomes negative. So negative 10.018. So that is expression 5, equation number 5. Okay. So remember, the first and the last. Okay, the first equation I equal to 0, and the last equation somehow you will replace, you will counter, or you will produce the y term which is not in your grid of solution, but somehow there is the representation to that out of the grid node. Okay, so based on equation 1 to 5, we can form the system. Okay, if you want to write in terms of a matrix, okay, then we'll have this one like this. From equation number 1, so you see equation number 1, you have negative 2.25 y naught plus 2. So negative 2.25 y naught, and y1 is 2. Okay, so we don't have y2, y3, y4. So 0, 0, 0. Okay. And our unknowns, again, y0, y1, y2, y3, y4. Okay. 5 by 5 system. Okay. So maybe you want to put the right hand side term first. Okay, from equation number 1, 1.175, equation 2, 0, all of them 0 except the first and the last. So 0, 0, negative 10.018. Okay, so the coefficient matrix, okay, from equation number 2, you have 1, negative 2.25, 1, 0, 0. From equation number 3, you don't have y0, so put as 0. So this is 1, negative 2.25, 1, 0. Equation 4, you don't have y0, don't have y1, 1, y2, negative 2.25, and this is 1. And finally, equation number 5, you don't have y0, don't have y1, don't have y2, y3 is, coefficient of y3 is 2, and then negative 2.25 here. Okay, so you will end up with 5 by 5 system here. So the suitable method that you can use here, you can use Thomas, because you can see the matrix A, the coefficient matrix here is in the form of tridiagonal matrix, okay, which is the special or the specific criteria for the Thomas, okay, Thomas algorithm. Or basically you need to follow, what the question asks you to do. Okay, if the question asks you to solve using the Thomas, then you need to follow. Okay, but for now, I just give you the final answer here, right? Why not equal somehow? Okay, so later you may want to find the complete solution based on the Thomas, or even you can use the Gauss elimination if you want. Okay, so y2 y3 and finally y4. All right, so those are five steps basically in solving the BVP, which contains the derivative in its boundary conditions. Okay, so this is important part here, to discretize the boundary condition. Okay, but depends. Okay, sometimes only one of the boundaries, okay, contain the derivative, the other one does not. Okay, so need to be careful here. Okay, so if it is contain the derivative, then the boundary, the value at the boundary will be unknown. Okay, but for example here, if you are given y1, okay, y1, okay, without the derivative, y1 equals 1.175, then yes, you can put straight away y0 is 1.175 here. Okay, so look carefully at your boundary condition. Okay, sometimes one of the boundaries do not involve the derivative. Okay, sometimes only the left boundary, sometimes only the right boundary, and sometimes both of the boundary conditions contain the derivative. Okay, um, okay, so I think that's it for the boundary value problem with the boundary conditions that involve the derivative. Okay, so I hope you can understand the all the steps, okay, in solving this BVP problem here. Okay, so that's all for now. Thank you so much. Bye bye.